CGL, Central Gem Laboratory, is a gemological laboratory established in 1970. Our laboratory is largest in Japan and has offices in Tokyo, Osaka, Nagoya, Hakata, and Kofu in Japan. Our services are the diamond grading, colored stone identification, research, and education. I belong to research section and study beryllium-diffusion corundum and origin determination by using LA-ICP-MS. CGL has a variety of analysis devices. For example, diamond view, Raman spectrometer, EDX-RF, UV visual spectrometer, FTIR microscope, and LA-ICP-MS. Recently, we lay emphasis on identification of mounted metal diamond by using the original machine that CGL developed. By the way, I moved today's main theme. Since September 2001, some vivid color sapphire, such as orangey red, orange, pink, and yellow, have appeared on the market. It is a concern of the jewelry trade that a large amount of orangey pink to pinkish orange paparacha-like sapphires are distributed, and most of them have been found to be treated with beryllium diffusion. Sapphires in this photograph are beryllium-diffused sapphires. Beryllium-diffused corundum are seen from 2001, but we can still see it over the decade. Beryllium-diffused treatment means the technique beryllium diffused into the corundum from surface directly. When corundum is heated with powder of chrysobel, beryllium from chrysobel diffused into corundum, and corundum changes its color. In pink sapphire, beryllium diffused layer becomes orange, and it can be seen as a paparacha color. Here is an explanation between traditional heat treatment and beryllium diffusion treatment. Left figure shows schematic drawing of the traditional heat treatment. Under the heat treatment, an inclusion in corundum melted and elements included in it diffused into corundum. This heating is done at 1400 to 1800 degrees of temperature. Right figure shows the diffusion from outer sources. Elements in materials surrounding corundum diffuse into corundum. The beryllium-diffused corundum treatment is the case of this treatment. When the corundum heated, elements from outer sources diffused into corundum, and corundum changes its color. This heating is done over 1800 degrees of temperature. Beryllium-diffused treatment is usually done after preforming, and most of stones shows observed surface conformal layer. If a surface conformal layer can be observed, this stone is diffused elements from outer sources. However, in some stones, beryllium has diffused in the whole region and colored uniformly into the inside. Such stones do not give the color zoning shown in this photo. In diffusion from outer sources, before the appearance of beryllium diffusion treatment, there has been a surface diffusion treatment, titanium and chromium. It takes 600 hours at 18 degrees of Celsius for 1 millimeter diffusion of titanium and 5,000 years at 18 degrees of Celsius for chromium. Since the diffusion rate of titanium and chromium are extremely low, they diffuse only the surface of a crystal, thus can be observed under optical microscope. The diffusion rate of beryllium is very high, and it takes 4.8 hours at 18 degrees of 1800 degrees of Celsius for 1 millimeter diffusion. Therefore, beryllium may produce a surface conformal layer or even diffused throughout the stone. To detect the trace level of beryllium for identification of beryllium diffusion treatment, SIMS, LA-ICP-MS, and LIBS are required. We explain how to identify beryllium-diffused treatment. One of the characteristics in beryllium-diffused corundum is a surface conformal layer. A surface conformal layer suggests that this stone was treated and colored artificially. A surface conformal layer cannot be observed in blue sapphires, but beryllium-diffused blue corundum may have rows and strings of circular inclusions that may resemble corkscrew like this photo. High temperature heating does not always suggest beryllium-diffused treatment, but is suspected beryllium diffusion treatment. Inclusions in these photos suggest the corundum heated in high temperature. In general, beryllium-diffused treatment is undergo in high temperature, so we must be careful observation of inclusion in import is important, which suggests high temperature heating. Beryllium-diffused treatment cannot be identified by eye observation if the conformal layer or unique inclusion is not visible. Therefore, we must analyze beryllium directly. EDXRF, which used widely in gemological field, cannot detect beryllium. Because beryllium is a light element and diffused in lower content. To detect beryllium, we must LIBS, LAICP-MS, and SIMS. Those can detect light elements with high sensitivity. In gemological field, LAICP-MS was used to detect beryllium. We introduced LAICP-MS early and used it to identify beryllium-diffused corundum. LAICP-MS is abbreviation for laser ablation coupled plasma mass spectrometry. This instrument is able to detect light elements such as lithium, beryllium, and boron, and high sensitivity of ppb to ppm, analyzes elements quickly, and analyzes multi-element simultaneously. This is a flowchart of beryllium-diffused corundum identification. At first, corundum is identified by standard identification method. If a corundum has surface conformal layer, it is beryllium-diffused. If heated, we call customers if they want to analyze their corundum by LAICP-MS. We analyze corundum by LAICP-MS only if customers allowed. I introduce our LAICP-MS system. LAICP-MS system consists of two instruments. In CGL, we used New Wave UP213 for laser ablation and Agilent 7500A for ICP-MS. At first, I explain mechanism of laser ablation. The left figure shows schematic drawing of laser ablation system. This instrument includes a sample chamber, a needle-YAG laser, and a CCD camera to monitor a sample. The right figure shows the sample chamber. When a sample is ablated by laser, a part of surface melts and evaporates. Argon gas flow sends evaporated sample to ICP-MS. This is the mechanism of laser ablation. Shorter wavelengths of laser has higher energy, therefore, 213 nanometer laser is used for ablation in CGL. A hole is formed on surface of the sample by laser ablation, but the marks of a few 10 micrometer, we can hardly find it in Lupe with 10 magnification. This test may be said a semi-destruction inspection because some damage is given to the sample. Therefore, we do this test after we got the consent of customer. Next, I introduce mechanism of ICP-MS. A laser ablated samples and argon gas come into the ICP-MS system. They go through plasma torch made of quartz. Plasma made by argon gas and over 6,000 degrees of temperature is created by torch. In plasma, samples are disintegrated into atoms and become ions. Ion lens draws ions made by plasma, and those are focused here. In magnetic field by quad pole, the target elements we want to analyze goes straight, but other mass cannot go straight and go out. Detector count target element which we want to analyze, so we can perform quantitative analysis. The summary of LA-ICP-MS is as follows. At first, it detects light elements such as lithium, boron, and beryllium, and analyzes very quickly. One-point analysis takes a few minutes and easy to change samples. Second, it can analyze elements in ppb to ppm order, but this instrument has two disadvantages. One is an ablation damage of some 10 micrometers, and the other running cost is high because we use argon and helium. Now, I talk about Japanese market. I show about 30,000 corundum certificated in CGL in 2014. This graph shows proportion of color of corundum. Blue sapphire is the highest in the proportion, followed by red, pink, orange, and yellow. In other category are included green, purple, and white. This proportion is thought to present circulation of corundum in the Japanese market. Blue sapphires and rubies are the dominant. 1.7%, about 500 in all corundum, were beryllium-diffused. The right graph shows the color variations of beryllium-diffused corundum. Over half number of beryllium-diffused corundum is pink to orange. Blue sapphires and rubies, those are dominant in market, are smaller in them. This slide shows proportion of beryllium-diffused corundum for each color. To be easy to look, this graph is cut at 40% in right side. The proportion of corundum samples is classified into 4 groups. beryllium-diffused corundum determined by LA-ICP-MS is shown in blue color. Beryllium-diffused as determined by standard identification method such as surface conformal layer is shown in red color. Green color shows corundum, which were not analyzed by LA-ICP-MS, although we suggested customers to inspect the stones by LA-ICP-MS. Purple color shows stones identified to be not suffered from beryllium diffusion treatment by routine techniques. Only 0.1 to 0.2% are beryllium diffused in blue sapphire and ruby, but about 10% are beryllium diffused in yellow and pink to orange. Many pink to orange beryllium diffused sapphire could be identified under optical microscope because they have a surface conformal layer. But very few yellow corundum diffused sapphire is identified by optical microscope. Green part in this graph is originated that customers can decide with LA-ICP-MS analysis is done, and it indicates that many yellow corundum are not undergo LA-ICP-MS analysis. This graph shows the comparison in yellow corundum in 2012 and 2014. In 2012, corundum not analyzed LA-ICP-MS is 24.8%, but 2014 is 15%. This data indicated that there is a tendency for customers to identify beryllium diffused or not. It is found that consciousness for the information disclosure to customers improves. These graphs show beryllium content versus frequency distribution by histograms. X-axis is beryllium content, and y-axis is ratio of frequency distribution. There are lower content in beryllium-diffused blue corundum. Pink to orange sapphires concentrate 10 ppm back and forth. It was found that beryllium-diffused corundum has about 10 ppm of beryllium. Are all corundum containing beryllium diffused? The answer is no. In early days of beryllium diffused treatment, the detection of beryllium was regarded as evidence of beryllium diffusion treatment because this element did not exist within untreated corundum. As a result of detailed study of advanced laboratories, some beryllium-containing corundum have been confirmed to be untreated. What is the difference between them? A little technical talking, I introduce the result of non-treated corundum containing beryllium. The example of sapphires containing natural origin beryllium is shown here. These are blue sapphires of basaltic origin from Huaisai in Laos, Pailin in Cambodia, and Mabila in Nigeria. In addition to beryllium, niobium and tantalum were detected in these samples. The contents of these elements are shown in this table, and they are traced. I examined the correlation between beryllium, niobium, and tantalum. Blue square shows the concentration of beryllium and tantalum, and green triangle shows the beryllium and niobium. After plotting, there are good correlation among them. Because beryllium is a light element, beryllium diffused into corundum by heating. But heavy elements such as niobium and tantalum cannot diffuse. Therefore, If these elements are diffused at the same time, we cannot recognize a good correlation among them. If there are a good correlation among beryllium, niobium, and tantalum, this beryllium is natural origin and existing in corundum crystal since birth. This is a corundum crystal, which has been identified to contain natural origin beryllium. It is a round mixed cut golden sapphire of 16.949 carat. This corundum has been heated, but it does not show features of beryllium diffusion process, such as the surface conformal layer. This is a table showing concentration of trace elements. Beryllium contents varied depending on the location, from 7.14 ppm to 1.42 ppm. It is noted that zirconium and hafnium are also detected. Shen reported in 2009 that there are correlation between beryllium, zirconium, and hafnium. I investigated the correlation of beryllium, zirconium, and hafnium that were found in this corundum, which were proved to be in a good correlation. Here is a summary of the identification of corundum with natural origin beryllium. No surface conformal layer is found. Beryllium contents vary largely depending on the measured location. Trace level of niobium, tantalum, and thorium are detected with beryllium in blue sapphires. Trace level of zirconium, hafnium, and tungsten are detected with beryllium in yellow sapphire. And there is a good correlation between beryllium and these trace elements. In the end, I introduce other application of LA-ICP-MS. LA-ICP-MS detect light element in ppb to ppm order we used for identification of natural and synthetic ruby and origin determination. At first, I talk about natural and synthetic rubies. Recent years, it is difficult to identify natural and synthetic ruby with internal feature and microscope because some synthetic rubies were heated. There are differences of trace elements in natural and synthetic rubies. Synthetic rubies have some elements from flux and crucibles, and natural rubies have some element of natural origin. Because there are different trace elements among different synthetic methods, we can identify synthetic method of synthetic rubies. Next, application of origin determinations. Gem minerals have information about the geological environment of host crystal and occurrence. Analyzing the component of gem minerals leads to identify geological environment of the host crystal and occurrence. We use trace elements analyzing by LA-ICP-MS for identify origin determination of rubies and blue sapphires. We, Central Gem Laboratory, uses LA-ICP-MS for identifying beryllium-diffused corundum, synthetic rubies, and origin determination of rubies and blue sapphires, and further research based on measures of trace elements. Thank you for attention.